In this video, we're going to have a look at a newly discovered super-Earth, which is known as Ross 508b. We're going to have a look at the planet, how it was detected, and what's interesting about it in comparison to the thousands of other exoplanets that we've already discovered so far to date. So firstly, it's known as a super-Earth because it's a little bit bigger than the Earth and not massive enough that it's kind of a massive gas giant. So it's about 1.8 times the radius of the Earth, and that's the estimated radius. The way that it's been detected, it's quite difficult to get exact figures on, but it's almost 2 times the radius of the Earth. We don't have any direct images of it, which is why this is just purely a size comparison here. We don't have direct images of many exoplanets, only some of the very largest ones, and if they're a long way from the star. But we can get an idea on their general sizes and their orbits and things like that. Now, it has a minimum mass of about 4 times that of the Earth. Now, why is it a minimum mass? Again, it's down to the detection method and how it was discovered. We can't get an exact mass on it, but we can constrain a minimum mass on that, and it's about 4 times that of the Earth. It's also worth noting that Earth is the densest planet in our solar system, and this particular planet is not as dense as the Earth, and it's kind of a bit less dense given those parameters of the planet are correct, and it would make it a bit more of a puffy planet, low density one, maybe with an extended atmosphere, which is fairly common for these super Earths, so they can be a bit more of like a puffy planet. Now, the star that it orbits is Ross 508, and it's an M-type red dwarf, and it's about a fifth the radius of the Sun. So again, size comparison there shows that it's quite a small star. It's obviously a very cool star as well, so it has a cooler temperature. And to put that in context again, it's almost half the temperature of the Sun. So it has a surface temperature about 3071 Kelvin, whereas the Sun is about 5700 Kelvin, so almost half the temperature, which makes it red. So the cooler stars than the Sun are a redder colour, and if they're hotter, they go more towards the white and blue part of the spectrum because it obviously relates to their temperature. So it's a cool star, not very big. It's not going to give out a huge amount of energy, which is important actually for what we're going to have a look at for the properties of the planet. Now, it's only about 37 light years away from us, which in astronomical terms is not that far away. It's not hundreds and thousands of light years away, so it's relatively close in our neighbourhood. That doesn't mean we can go and visit it relatively easily. It's still out of our reach, but in astronomical terms, it's relatively close. Now, the habitable zone is only about 5% the distance as our habitable zone. So our habitable zone is essentially where we are, where the Earth's orbit is, and the habitable zone for Ross 508 is only 5% the distance of our habitable zone. And just to recap, the habitable zone is the location or distance from a star where you're going to get liquid water. So this is very close to the star, and this is purely down to the fact that it's a small star, not a very hot star. So it's not giving out a huge amount of energy in comparison to our Sun. Again, putting in context of our own system, this is only about 1/8 the orbit of Mercury. So Mercury is very close to the Sun in our system, but the habitable zone of this particular star is only 1/8 the orbit of Mercury. So again, this is very, very close to the star in comparison to our own system. Now, a consequence of that is that its orbital period is just less than 11 days. So it's a very, very short orbital period to go once around its star. And the very intriguing thing here is that it's expected to have a very high eccentricity. So it has a very elliptical orbit, which is unusual really for planets. None of our planets have particularly elliptical orbits. They're quite close to circular. Yet we have a planet here which has a very elliptical orbit of about 0.33. So very unusual there. Now, if your eccentricity is 0, then you've got a circular orbit. And most of our planets, including the Earth, are close to 0. They're not 0. They are slightly elliptical, but they are quite close to being circular. And if you go to 0.5, then it becomes a lot more elliptical, like this. And then if you go beyond that, so if you go greater than 1, then you've essentially got a hyperbolic orbit. And it's not really on a bound orbit then. It's essentially coming by and making this movement here. And that's just to put into context of how elliptical this particular orbit is for this planet. So the consequences of having a high eccentricity or elliptical orbit is that the amount of radiation reaching the surface of that planet varies greatly during one orbit. So remember that orbital period was just less than 11 days, and this is a plot here from the Discovery paper, and it basically plots the star temperature of various planets and their insolation, which is essentially the amount of solar radiation reaching a given surface in a given time. So it's essentially the energy reaching the surface on a planet. So you can see there straight away, Ross 508b, which is the red horizontal line, shows that it varies a lot. There's a huge error bar there, mostly down to the fact that it has a high eccentricity. So it's moving in towards the planet, in towards the star, and out again over about 11 days. So that varies the amount of energy that's falling per surface area per given time, compared to all those other planets that you can see there. Now, that's likely to give you extreme seasons. Now, I'd put kind of snow at the top there, but if you have a look at the actual planet itself and the habitable zone, then it's not likely to be probably that cold because it's moving inwards and then into the habitable zone. So it's likely going to get a bit hotter. But the point being, you're going to get quite extremes of temperature, which is going to drive some quite wild weather on this particular planet, because you're going hot, cold, hot, cold. That can drive huge winds, and you're going to get some very interesting things occurring there due to that particular orbit in and out of that habitable zone. So why does it actually have a high eccentricity? Well, planets generally form in a disk around young stars. So when they're forming, they form kind of in this disk while the stars are still forming. And that process doesn't generally yield orbits that are very elliptical. So there is some interaction between the planet and the disk, and you can get some elliptical orbits, but not extreme elliptical orbits like what we might see here with this particular planet. Now, one process that can give you that high eccentricity for an orbit is if you have more than one planet. So in multi-planet systems, you get migration occurring. So planets can wander about, they can move inwards and outwards. And if they pass too close to each other, they can perturb each other, and you get what's known as a gravitational scattering event. Now that can change the orbits of each of the planets. So when they get too close to each other, they can scatter planets outwards, inwards. It also gives a elongation of their orbits. So it makes them more elliptical. So that's one process that can happen. On extreme cases, the planet can actually get ejected from the system, and that is then known as a rogue planet. So you have these planets floating around in space that are not hosted by a star. So this is what's known as a rogue planet. And then you're left with a system with one less planet, and with maybe one in that system would have a higher eccentricity than it would have done normally because it was scattered and that remained on the star, and this other one was then ejected. However, Ross 508 to date doesn't have any other planets orbiting it that are known. So at the moment it's a single planet system, but that doesn't necessarily rule out that maybe there was a gravitational scattering event that did occur. Maybe a planet was thrown out, but it's no longer there. Or something's happened, we can't see it, it's not there. Or it never actually formed with a second planet anyway. We don't actually know. But the point is, we don't have more than one planet in this system that we know about to date. So other super Earths around red dwarfs have been found to have high eccentricities as well. So there could be a common cause here that's causing this particular group of planets orbiting this particular type of star. So further, more detailed observations can be made which may reveal the cause. We may get to find out how they kind of formed, where they originated from, and they're likely going to have a common cause. And that will be exciting to find out what's forming these particular types of planets. Now, how was it actually detected? Well, it was detected using the radial velocity method by the Subaru telescope. Now, the radial velocity method looks at the light from a star, and it looks for a Doppler effect on that. So the planet orbits the star, well, it actually doesn't orbit the star. They both orbit a common center of mass. Now, because the star is so much more massive than the planet, it has a smaller orbit. And when you look at the star, it appears to move away from us and towards us. So we get a blue and a red shift of that light, which we can measure. And you can see here that the light moves, the spectrum moves to the left and to the right. And then that's what we're measuring. We're measuring the velocity of the star by looking at its light from the Doppler effect, basically. Now, this is the plot of the radial velocity of the star for Ross 508 from the Discovery paper. And you've got one orbital period there. And you can see that actually the radial velocity of the star increases and decreases during one orbital period. And it peaks around about 5 meters per second. And that is fairly straightforward to get one orbital period. The velocity of the star can help us constrain the mass. Again, it gives us a minimum mass because we don't actually know the orientation of the orbit. So depending on how it is as we look at it, it's either edge on or not edge on. So we don't know the absolute peak of that velocity. So that's why it's a minimum mass. But this is how it was discovered. Thank you for watching. And if you enjoy, then go check out some of the other videos.